Hello, and thank you for joining us for today's EC event, the Automated Cell Deep Dive. My name is John Einberger. I'm Product Line Manager here at Makino. Before we get started, just one logistical item. We'd like to get questions from you during the course of today's event. We're going to address those questions at the end of the event, but the way for you to get them into us is to use the chat function that's in the upper right-hand corner of the screen that you're watching us on today, right there circled just as an example. So without further ado, let me introduce Mr. Dave Walton. Dave is the Director of Engineering Operations here at Makino. Dave, can you tell us a little bit about your background, particularly when it comes to automated systems?
Sure. Been with Makino for around 25 years, and during that time frame, I've been involved in the automation surrounding our machining centers, the automating of our machining centers and the machining process throughout the course of that 25 years, dealing with the design, implementation, and installation of those systems.
Certainly one of the strongest areas of growth that we see on a year-over-year basis. Today's agenda is very simple. We're going to set the background, talk a little bit about what we're trying to accomplish with this particular cell that we're going to profile, and then jump right into the details, take the deep dive, and look at a variety of different operational aspects of this particular system. So first and foremost, what are we trying to accomplish? What were we looking for here, Dave?
So when we set out to design this system or implement this solution for our customer, what we're looking to do is provide a highly efficient, reliable system that is able to produce parts at the rate required and provide the quality of the parts that's required.
In particular, we're machining differential carriers. If you're familiar with a lot of, let's just say, pickup trucks, delivery trucks, things of that nature, something that you probably see when you're behind them in traffic, but think about it as the big pumpkin that connects the two axles at the back of the vehicle. In this particular case, the customer needed a cell that had the ability to produce 100,000 parts per year. From a machining standpoint, about 21 minutes per piece is the total machining time. What that equates to, this particular cell, 8 total machines. So if we take a look, a little bit more detail, ductile iron parts, so very big, very heavy. Think about that in combination with the volume and the takt time.
The ergonomic issues that are associated with handling such a large part that's got a difficult to handle, multiple machining operations that we're dealing with. So, those things we all take into consideration when we're designing the cell.
Absolutely. So ergonomic issues, wanting to create a safe environment for the people working in the factory, reduce those injury possibilities. But bearing in mind also being a differential carrier, they're very precise pieces, right. Very precise work pieces. Summary?
So looking at, as we lay this cell out, obviously it's a very good fit for automation based off the fact that we've got multiple machining centers, based off the production requirements for our customer. We have multiple orientations of the part where we're handling this, multiple machining operations and auxiliary operations, and tack in the large part, the difficult to handle part, and it just made a good candidate for automation, machining automation.
We mentioned before, based on the cycle time, the machining requirements, a total 8 machine cell. Dave, we're going to see a little bit different variation of this setup. Specifically, if we start out with what we're looking at here, this is more akin to what we're going to see set up here in profile today. Why the difference? Why something less than the entire system here at Makino Mason?
So what we try to do here at Makino Mason, before we go to the customer's floor, before we take and implement the full automated machining cell, what we want to do is we want to set the cell up here with all our engineering resources, and we want to test and integrate each one of the different operations, whether it be the machining operations or the auxiliary operations, into the system here so we can test it, and then we can duplicate those operations that are just duplicate operations. We can duplicate that and implement them on our customer's floor. But we're able to test and confirm the operation of the cell here on our floor before the installation at our customer.
So at the customer site, that entire 8 machine cell will then be run off?
Correct, yes.
Take a little flyover view of the 2 machine subset, if you will, moving from left to right. And we'll profile all these different pieces of equipment here as we get into the deep dive aspect of today's discussion. So just kind of give you an idea of what that system looks like, what the setup looks like. Pretty consumptive from the standpoint of even setting it up here.
Right. You see the fencing, the coolant containment panels, everything associated with that cell is set up here on our floor.
Let's start out with the most basic element, Dave. How are we moving parts throughout that cell once the operator drops them off?
For this particular application, we chose an overhead robot system. What this provides, a couple things. Easy access to the front of the machine, so the automation's up overhead, so if you need to get access to the machine, the machining center, you can do that quite easily, quite effectively. And there's less trip hazards in the cell, easier to clean, to keep the cell maintained over the course of the program.
One operational aspect to point out, even though we're looking at a family of parts that are all very, very similar to each other, there are multiple part numbers, if I recall correctly, Dave. Is that accurate?
Correct. This particular cell can accommodate 3 different part numbers, and it can run 2 different part numbers at the same time. So you can have 4 machines running one part number, and the other 4 machines running a different part number.
So if there is a level of changeover that's required to go from one part number to another, again with that overhead robot on rail, very easy access to the front of the machine, safety lockout and what have you.
Correct.
So let's look at the input, the parts coming into the system, the input conveyor. Now we know how we're moving them. Let's start getting the parts into the system.
Right. So as we have selected what we call a fixtured input conveyor. So there are multiple fixtures on this conveyor that hold the parts in the orientation required to load directly into the Op10 machining operation. And once again, we went with a fixture conveyor because of the odd shape of the parts and putting them in the orientation that we want to load them into Op10.
Typically, Dave, when we're designing a system of this nature, what kind of inputs will the customer have as far as how they want to run it and how big that input conveyor ends up being?
Yeah, typically what we want to understand from our customer base is how much unattended operation do you want? 30 minutes, 60 minutes, do you want to run it through lunch breaks? Do you want to have a more extended period where the cell will be able to run unattended? Because then that allows us to size properly the amount of input buffer that we provide for automated cells.
Certainly a balancing act from the standpoint of how much floor space that input conveyor takes versus that unattended time that
Correct.
The customer is looking for. Correct. So we have the parts in the input conveyor. Obviously, we've got the robots to move them around. The interface in between the two is going to be the gripper. Let's talk about that a little bit, Dave.
Yeah, so here we have what we call a dual part gripper because we've got multiple orientations of the part that we're gripping. This is the Op1020 gripper where we're gripping on the internal cavity of that differential carrier. And since we're picking up on a cast surface, we've got finger compliance mechanism built into this gripper to accommodate the variations that we'll typically see in a ductile iron casting of this type.
So that device strokes out, the certain amount of stroke is the same each time. You've got compliance built into the part touching details themselves.
Correct. So we get a good grip on that part for transportation.
You mentioned other operations, Operation 30.
So Operation 30 here we're gripping on the outside on the axle tube collars of the part. We're also once again on the outside gripping on the outside of that part cast surface. But here we've incorporated what we call an anti-rotation device because we don't want that part to move within the gripper once we pick it up. We once again trying to maintain that part accurately within the gripper while we're transporting it and loading it into the machining center.
So a lot of detail built in right there on the front facing. Let's take a look at the back side of the gripper. A couple of things to talk about here.
Right. So in each one of our robot grippers, we incorporate a complete set of sensors. So we're going to check to see that the part's there in the gripper. We're going to provide the status of the gripper, whether it's open, whether it's closed. Sometimes if it's open with a part and open without a part. So what we're trying to do is we're trying to monitor the status of that robot gripper throughout the whole operation of the robot within the cell. And we monitor that continuously, and if something changes, then we'll stop the operation and we'll enunciate an alarm for the operator to come make a disposition on what's happening.
So we're tracking the movement, we're tracking all these activities, if you will, through the logic that's programmed in, but this really is verification that what we think is happening really in trueness is happening.
Right, correct. So we've got complete control of the part with the automation. We are tracking it through, but we're also confirming where those parts are with these sensors.
Okay, data coming in, data going out. How do we handle that to the gripper, Dave?
Right, so now we have all these sensors. They've got to be wired back into the robot controller. So what we like to use is a consolidated I/O junction block, which improves the reliability of the gripper, of the operation of the gripper. We have a single cable going back through the robot arm that we have to control. So we have to control all those different signals going back through the cat track that's attached to the robot, so better cable management.
So as you'll see as we get into some of the live videos of the robot in action, how much articulation there is really by minimizing the number of leads, the number of cables coming back through methodology like this, uptick in reliability.
Absolutely, absolutely.
With that said, let's get into the machining side. Let's start that first machining operation. All of these machines are set up to do one of the two machining operations on the first pallet. We'll profile that right now, but bear in mind, each of those machines also has the ability through its second pallet to do the second machining operation that we'll profile in a moment. I want to talk for a moment about the machines that were selected for this particular program. They are the Makino A81NX horizontal machining centers, 630 millimeter pallet size machine, Cat 50 spindle in this particular case, but they've fitted with multiple retrofit options to facilitate automation. Let's talk a little bit about those options.
Right, so with the 1 series machines that we have developed a suite of options that support automated operation. The first one being auto doors. So we want to automate the access to the fixture for the robot to load the part in and out of the fixture. And what these doors do is it provides protection from the operations, manual protection in case an operator is in the area for fixture clamp, the pallet change operation. But what it also does is it contains coolant, and we'll show you why that's important here in a minute.
Very good point. That brings up the next operation of fixture wash.
Right, so you don't have that operator in front of the machine, so now you need to be able to clean that fixture off, get the chips. You want to keep the chips in much cool as you can there inside the machine. So what we're going to do is we're going to add this what we call fixture wash, and what it does is it flushes the fixture before the robot comes in and unloads the part, and then after the robot has unloaded the part, we're going to flush that empty fixture to get as much chips off of that fixture as possible.
So think about this as high volume coolant from the outside in. Let's look at the converse to that. Let's look from the inside out.
Right, along with our fixture wash, we have through fixture coolant. So what we're doing here is we're running coolant down through the rotary union, and then we're running it to spray nozzles that are very close to the locating features in the fixture, or areas in the fixture that would typically accumulate chips that you want to keep those chips from accumulating. This is something that we can turn on at the discretion of the NC program or have it on continuously.
So low volume coolant, but very, very directed. Last one, let's have the machines communicate with the cell control robot interface.
Right, so what we've developed over the years is a standard robot interface. That robot interface contains all the set of signals that we have run into over the past 25 years. So if you look at our standard specification, it'll accommodate well over 90% of the applications that we've seen.
And then the ability to customize on top of that to round things out.
Correct. So that what's really important is that if we do run into a special application, we can customize that software here and quickly for our customer.
Yeah, that's one thing that's very unique about Makino, and that we have engineering staff here on site that covers this North American, South American market that we have responsibility for. Really easy for us to make changes to customize something like the robot interface to make it application specific.
Right.
Okay, going back to the cell, talking about the first operation machining, operation 10. From the standpoint of features, cast locators, so that raw parts coming in unmachined, going to be located in the work holding fixtures. We'll get back to bearing caps in a little while. Keep that in the back of your mind, but they're not in place yet. We need to create the features in the part that allow the bearing caps to be assembled to it for future machining down the road, and also process a majority of what I'll call the periphery features. So with Op 10, Dave, let's look at the load cycle. Start out with this. If you would, describe what we see going on here.
Yeah, so right there, what you're seeing is we picked the part up off of the conveyor, the fixture to input conveyor. We're going to set it on that regrip stand because we have multiple fixtures on our input conveyor, and so we want to make sure that we've got the best grip on that part prior to loading it into the machining fixture. And so what we do is we set it on that stand where we know we're going to get the same orientation of that part every time. Just drop it off, unclamp it, reclamp it, and then load it into the fixture.
That's one of the areas where when we're gripping on cast details on the part, over the lifetime of the casting tooling that's used to make those parts, we do see a level of variation of part to part to part as that cast tooling wears over its lifetime of being used. So we want to be very precise. So set down, ungrip, regrip, put it back in the machine. Really aids in that reliability of loading.
Over time, absolutely.
So the loading's kind of interesting, but I think the unloading in Operation 10 is probably a little bit more interesting. Let's profile that, if you would.
Okay, so what you're going to see here, the robot's going to come in and grip the part. Now the first thing it's going to do is it's going to kick that part out because we have part detents on the Op10 fixture that holds that part in place. So it's going to rotate it up in order to clear the part detents in the fixture. And now what it's doing, it's going to go through a series of moves that's going to dump that coolant out of that part. There's a lot of internal cavities in that part. A lot of coolant's going to collect within that part. We want to leave it inside that machine. And so we're going to rotate that part around in a couple different orientations to try to get that coolant out of there, let it sit, let it drain. You can see we provide coolant containment pans in the cell, but we're once again trying to keep that coolant inside the machining center.
So think about the upfront engineering work that goes into laying out a system of this nature, sizing a system of this nature, because all of those operations that the robot are performing, they take cycle time. And we have to be very mindful of that from the standpoint of having the robot not be the limiting factor to throughput of the overall system.
Correct. When we lay a system out, one of the most important criteria that we do is the robot cannot be the bottleneck. So we will look at the cycle times, we will look at what the throughput requirements are, what the takt time is for a part to come out of the cell, and make sure that that robot can keep up with that.
So continuing on through the process, as Dave has articulated, the dumping of the coolant, following the kick out from the part detent devices, and I'll take it over to drop off for what we'll profile in a moment, the Operation 20 series of activities.
Right.
With that said, Operation 20 loop. Operation 10 was machining. We need to do some things to these workpieces in between the first Op10 machining process and the follow-on Op 30, that's Operation 20. There's a series of activities that we're going to profile. But let's start with getting the part into the Op 20 system.
Right, so right here what you're seeing is you're seeing the robot. It's going to set the part onto a fixtured pallet. So we have a series of pallets on our pallet conveyor that contain a fixture which holds that part in the orientation required for the auxiliary operations that it's going to be going through while it's on this pallet conveyor.
Is there any tracking that's done? Multiple pallets, we can see them in the view right now. We see the pallet that the part was set on. We have a pallet that's behind it ready for the next part. We have a pallet around the corner that's ready. Are we tracking anything in particular about those specific pallets, Dave?
Yes, because we're able to run multiple part types through the cell, so we need to know what part type was set on that pallet. So there is an RFID system with a chip attached to each one of the pallet. So we know, put on pallet number 32, that we've put part type 1 on there, and that's tracked throughout the whole pallet conveyor system.
So Operation 20 loop, I mentioned that there are a number of activities that happen in it, part inspection, bearing cap installation. If you think back to where we were early on in the presentation, I said that in Operation 10 we're creating features that allow assembly of the bearing caps and then part marking. Let's start with a more detailed look at that first step, the part inspection.
Right, so what we're doing here is we're inspecting for critical features in the part. So we're going to bring the part in, we're going to locate it. You saw that small lift up, so we've got a good location of that part. We're going to take a couple pictures of the part. The next screen here will show you those features that we are making sure that was completed in Op 10. Even though we've got monitoring devices such as broken tool sensing in the machine, our customer wants to make sure that if there's anything that's missed in that operation, including threads, because we can check for threads that are in the hole, we want to ID that and kick that part out.
So to expand on that a bit, the A81NX comes standard with Vision broken tool sensing. We're looking at the integrity of tap drills after their use, the integrity of taps after their use. But in this particular case, it is so critical to this customer never to ship a defective part to their end user that they wanted another level of basically verification.
Correct, yes.
Bearing cap assembly, one of the things to think about with a differential carrier, the bearing caps will be machined as part of the follow-on precision machining operation that we'll profile in a little while. We need to get them assembled, we need to get them in place. Anything in particular about this station, Dave?
Just a manual assembly station. The bearing caps, the operator puts the bearing caps on. There's torque guns that he brings down. He torques the bearing caps in place. After they're torqued, he hits the finish button, and then the pallet's released onto the next station. So very simple. In
some particular cases, that could be an automated system. In this particular case, right, customer's desire was to keep that a manual operation. But we'll go now to the third stage, laser part marking.
Yeah, so what you see here is the part being transported into the laser marker. The door will close prior to the marking operation. And what we're putting on this particular part is we're marking the bearing cap and we're marking the carrier. To ID, that bearing cap goes with that side of that carrier and that side. So you see an orientation mark that's also put on that to make sure after the caps are disassembled, they are properly reassembled after assembly of the carrier.
After the machining in this particular cell that we're profiling, that part goes down to an assembly operation outside of what we're providing. The caps need to be taken off, bearings installed, other internal components installed. Very, very critical to get the right bearing oriented correctly. You have two choices. You need to pick the one choice that is accurate, but also the left cap needs to stay on the left and the right cap needs to stay on the right.
Right. And then we're also putting a 2D matrix on the part. This barcode includes the time and date stamp, and it also includes the part number, the part type that it's currently marking.
So readable through scanning devices later on.
Correct. This is a way to track when the part was made and what the part type is later on in the process.
Very good. Okay, so we're done with Op 20. Take the parts back into the machining area. Let's go on to Op 30 machining. We're going to be using machine locators now. Previously in Operation 10, we used cast locators. Here we're going to use some of the feature content that was created in Operation 10 to locate the part very precisely on the fixture. The bearing caps have been installed already for from Op 20, so they'll be machinable in Op 30. And we're going to process a majority of what I'm going to call the functional features. If you think of the input shaft coming in to the diff carrier and the two output axle shafts going out, all of the functional aspects of that will be machined in this particular operation. So let's take a look at the part loading.
So here you see the robot has picked up the part off the Op 20 pallet conveyor. It is now setting it on a regrip stand because we have to change how we're gripping that part prior to loading into the Op 30. So it sets it down with the Op 10 20 gripper, and then it's going to rotate around and it's going to pick that part up with the Op 30 gripper.
So same regrip stand that we used for the Op 10 part loading, but instead of setting it down, ungripping and regripping on the same feature set, after the ungrip, we go around to the opposite side of the part. But Dave, I see that we're still picking up on cast locators, but we want to locate on machine locators. How do we accommodate that potential mismatch?
Right, so with the variability, once again, we're picking up on a cast surface. What we're going to do is we're going to present that part to a camera. So we're going to look at those features on the part that are going to be used for location on the machine locators in the fixture. So what we're going to do is we're going to take that picture and we're going to offset that loading point for the robot into the fixture to accommodate any variability in that casting.
So the system knows where those features should be based on the robot position. It's going to look at where those features actually are and do that offset accordingly.
Correct, yes.
So go ahead and proceed with the fixture loading, and you'll see how just very smooth that is. That robot is not finding its way into the fixture. It basically is just a straight on
load onto the locators, yes. And you'll see here we clamp while the robot's holding the part. We clamp this part because it does not have part detents on it, so that we have the capability also of loading the part, having the robot hold the part during the clamp and unclamp operations.
So a little bit different than where we did the Op 10 loading, load the part, go away, fixture clamps.
Correct.
Here we're loading the part, unclamp the fixture, then go away.
Right. We relax the robot drives axes in order to allow the part to seat properly into the fixture.
Okay, we're done with machining. Parts washer. We didn't see a parts washer in the cell installed here at Makino Mason. Why would that be? Why would that piece of equipment not hit the floor here?
Yeah, really it's just an output conveyor, very simple piece or operation, integration into the machining cell automation. So as long as we know we have clearance and we've got an area to set the part down, it's something that has a low risk, and we really don't add any value Makino from the part washing functionality of the system. It's just we need to make sure we get that part set down properly on the conveyor system.
Think about it typically from the standpoint of the timeline associated with the program. That parts washer is very often going to be a custom designed piece. It's going to be a runoff at the parts washer manufacturer. So typically we'll be producing parts, we'll be producing dirty parts on purpose and sending them off to the customer designated location where that parts washer work is being done, so they can use those real produced machined parts that are dirty to do their cleanliness checks, things of that nature.
Right, right.
Let's look a little bit more gauge reject conveyor. What is that for, Dave? What does it do, and how does it integrate into the system?
Yeah, so in each one of our machining cells, we incorporate what we call a gauge reject conveyor. Sometimes it's the same conveyor as it's shown here in this particular cell, and sometimes we separate those two functions. We have a reject-only conveyor and a gauge conveyor. But what this allows you is to set up gauge frequencies, or if you're using a tool for the first time and you want to get that part out and gauge it, we've got a location that you can inform the automation, I want that part to come to my gauge conveyor so I can inspect the part prior to continuing to machine other parts. For the reject aspect of it, as we talked about before, we've got the visual inspection. We have monitoring systems on the machining center, such as our broken tool sensing systems. And if something happens and the part is not completely machined on the machining center, we've got a place to take that part and we'll flag it as a reject part because it's not a completely finished part.
So keeping that cell in operation, in the case of a broken tool, many times we'll work with customers to set up spare tools. Barring that, even if the spare tool is used up, that machining center will stop operation, indicate an alarm back through the cell control system as well as at the machining center. The other 7 machines in this particular case stay in operation. Let's close out, Dave, by looking a little bit at the brains of the system, the cell control. What are we looking at here?
Yeah, so this is the main operation screen. So what our cell controller does is it provides the main user interface for the automation. And it manages the communications between all the automation and all the different machining centers and auxiliary operations within the cell. So what you see here is the main screen, main status screen, that's going to give you an overall view of what's going on with that automated cell. So first we have machine status. So for each one of the machines, and you can see there's 8 indicators on this particular screen. So for each one of the machines, we're going to give a status indicator as far as what that machine is doing. And you can also see off to the right-hand side of each one of the larger indicators is a 3 red, yellow, green indicators that gives the machine stack light. So it gives you immediate exposure to what's going on with the machining center.
Okay, so we certainly have the stack lights at the machine, but it gives somebody in charge of overall cell operations that one location snapshot of what's going on.
Correct.
Similar for the robot.
Yeah, robot status. So we have our robot status indicators. So it tells you green obviously means the robot's up and running. If it's not running, it'll be yellow and red based off the severity of the situation. In this particular cell, there's 2 robots, so this screen only shows 1 indicator. We would have 2 indicators, 1 for each one of the robots within that cell.
So highly customizable from the standpoint of the content that you can put on this screen.
We have our basic cell or screen layout that we start from, but as our cell changes, we're able to reconfigure this to accommodate the different cell configurations.
Okay.
Now we have our operator command box. So if the cell is not running and your operator needs to get it back up and running, we will provide commands. We will provide a sequence of commands on how to get that cell back up and running. So for instance, if we need to close a gate, reset the emergency stop circuit, we will inform the operator of the sequence of steps required to get that automation back up and running and online.
So right there online, not having to pull out the manual, what do I do now? Just
correct.
Ready access.
Right. If you have somebody who's fairly new to that area, we can step them through the process of how to get the cell back up and running.
Very good.
And then the robot control buttons, those are located down at the bottom of the screen. And what we're trying to do here is we're trying to keep that teach pin out of the operator's hands, right? So we want to get a smooth, effective operation of the cell, not having to bring a robot technician in. So what we do is we put the robot controller in remote control, and then you can cycle start, you cycle stop, reset faults, right here at our main operator screen.
So a lot of capability in that teach pennant, but not necessarily something that we want everybody associated with the cell having access to.
That's correct, because they can get themselves in a lot of trouble real quick. For each one of our systems, we do provide part counters, and we can set those part counters up in different ways, whether it be shift counters or just single day counters, 24-hour counters. But what this does, this will tell you how many parts are coming out of your cell. And then our auxiliary functions. So we want to provide you the status of all our auxiliary functions. So we'll have a button in the lower right-hand corner of the screen that will provide access to those other functions, such as the conveyor, the inspection station, the OP20 conveyor, the input conveyor. So we'll provide status of each one of those pieces of equipment through this particular system.
And then the ability to pull them up and grab more detail of them
correct.
At that point in time. Well, let's do that. Robot status.
If you press the robot status screen on the main screen, what you're going to get is you're going to get our robot status screen. So what this does is it gives you more detail about that robot. So you've got the IOs, the status of the different inputs, outputs associated with that robot controller. You've got gripper status, so it tells you what your gripper sensors are, so you can see what's going on with there. And then it's got duplication of the other buttons, some of the other buttons that you see on the main operator screen.
So in this particular case, if we look at that very top yellow pane, the teach pennant is enabled. Instructions below, turn off the teach pennant.
Right, right. So once again, we're going to provide that step-by-step sequence of how to get the cell back up and running.
Okay. Think back to when we talked about the gripper itself with all of the sensors on the gripper. That really is the output of what those sensors are reporting back.
Right. So if you don't know what the status of the sensor is, you go to this screen, and it'll give you a complete rundown of what the status of those sensors are. Robot control, duplication of the buttons that are on the main screen, so you can also control the robot from this screen.
So still continuing that thought of keep the teach pennant out of the cell operations staff's hands.
Correct. And then what we've added with this screen is robot speed. So if you want to, instead of running at 100%, you want to slow it down and run at 75% for some reason, you can do that very easily right from this screen. And then probably the most important button on this screen is the rehome button. So one of the main things is reasons of trying to keep the teach pennant out of the operator's hands is that if for some reason you need to recover the cell and you need to rehome the robot, you need to get the robot back to a safe starting position and you can't continue from where the robot currently is, we've incorporated our rehome feature. So you press the rehome button, what it does is it sets the speed of the robot at 15%, and then it recovers and brings it back to a safe starting point for the robot. So then you're able to fault reset, cycle start, and the robot will then continue on in servicing the machining centers within the cell.
So kind of similar to what we see at the machining center level with Auto Zero. Similar to that, it does things in a certain sequence, a very safe sequence.
Correct.
To get back to a known starting point.
Correct.
All right, that rounds out our discussion. What we'd like to do at this point in time, if you remember at the beginning, I talked about the chat functionality. Let's take a look at some of the questions that have come in, and we'll address them on a question-by-question basis.
Okay, we are talking here live, and we do have a number of questions that came in today, Dave. Let me go through them one by one and turn it over to you for answers. First question that came up, what would be the pros and cons of this type of system that you talked about today versus instead doing an MMC with 2 to 3 workset stations?
Okay, so really what we have here is we have two different types of automation platforms. So what we presented today is what we would consider a part handling automated system. And I like to basically divide our automation products into two different categories. One where we're handling the individual parts, we're loading them directly into fixtures on the machining centers. And then those that are handling, whether it be a pallet, a fixture plate, a small Aroa style System 3R type pallet, where you're moving the fixture with the part already affixed to the fixture. So with the part handling style of automation, you're not moving fixtures on and off the machine. You're typically dealing with a set of part types that it doesn't vary quite as much as you would in an MMC or a pallet-based type system, where you can get a lot of high mix of different parts as opposed to a high volume of parts, which is very typical for a part handling system. And it's also important to note that with the MMC and the pallet-based systems, your unattended operation, your buffer, is in the fixtures, in your pallets. With a part-based system, your unattended operation is in with the parts. So whatever amount of buffer that you've got as far as input material and available area to put your finished parts in, that's where you get the amount of unattended time with that automation. So really it boils down to high mix, low volume, which is typically what you see with our pallet-based systems, and then high volume, low mix, where you typically see that with our part-based. And it's important to note that with an MMC, you still have that operator loading the part into the fixture. So you still have that manual operation associated with loading the part.
Okay, very good. Dave, when would you use an overhead style robot versus a floor-mounted robot? What would be the differentiator there?
Well, a lot of times we have customers, and we talked a little bit about this in the presentation, where they want to have access, they want to have clear access to the front of the machine. In this particular cell that we presented today, there actually is a fence. There's a door in the middle, in between two of the four machines on one end that they can close, and they can take two of the machines offline and they can run it manually. So having that overhead robot, having that rail overhead, clears out that space in front of the machine. The one advantage that we see with the floor-based and the pedestal robot, particularly in the offerings coming from Fanuc, with the pedestal robot, you're putting that 6-axis robot on that 7th axis floor track, so you can put devices, part stands, auxiliary equipment on the end of the rail. And it also, and we didn't cover this in our video today, but we're able to, in many applications, to zone off the machines. So we can take a machine offline and continue to run the automation servicing the other machines in the cell while that one machine is offline, and you may have an operator or your service person in front of the machines doing something to the fixture or something on the front side of the machining center. So with that overhead and what we presented today, that machine zoning is a little more difficult with machines on both sides of the rail. If we put the robot on the floor with the floor track, we can then zone off those machines, have them on both sides of the rail, and give you effective access. But then again, you still have that rail sitting out in front of the machining center. So and sometimes it's just a matter of preference with our customers.
Dave, what was the throughput volume capability of that full 8-machine cell for this ductile iron differential carrier?
For this particular application, they were running 100,000 parts per year through that cell.
Any idea how many different part variants they ran through that system?
Yeah, we're currently set up to run 3 different part types. There is a slight fixture changeover on one of the parts, on one of the types of parts, but then they're also able to run 4 machines on one end with one part type and the other 4 machines on the other end with a different part type. So simultaneously, they can run 2 different part types through this particular cell.
So the ability to zone those machines off that you talked about just a moment ago, that really would facilitate the fixture changeover that would be required to go from the 2 similar parts to the 1 dissimilar part while keeping the other equipment in operation.
Correct. Absolutely. Yes.
Okay. I've got one more question that's come in. A question on a little bit more on the machine side, so I'll handle this one. Why the choice of Cat 50 versus HSK A63? The 881NX 630 millimeter pallet machine is what we at Makino will call a Cat 50 class machine. So the spindle tapers that are going to be offered are going to be that Cat 50, but with the alternative on the HSK side of HSK A100. This particular customer chose HSK A100, reason being the precision of the parts, and also there is some relatively high force side load machining in the overall process. And that's where HSK really tends to shine relative to the 724 steep taper. So this particular case, HSK A100 was a choice. With the 630 millimeter platform, given the very typical usage of that style machine, typically very heavy metal removal, very high horsepower spindle relative to Cat 40 class machines or HSK 63 for that alternative. We want the more robust nature of the bigger spindle bearings. It gives us a lot more dynamic stiffness in that overall assembled spindle. So hopefully we answered your questions today. If you have other questions, please feel free to reach out to us. Again, my name is John Einberger. Dave Walton joined me. We're both available through the Makino portal. And any other questions that come up, please let us know. Thank you for your time today. We appreciate you attending, and we look forward to talking to you again soon.
Thank you.